ladies and gentlemen, and welcome to a short video on implicit differentiation, section 4.9 in your notes from our calculus class. I want to get started today talking about a little bit of notation that we've been using in the past. If we have a function, this incidentally is not in your notes just yet, we're talking just about a little bit of notation, so you may want to write this somewhere that you can reference later. If we're talking about a function, for instance, y is equal to x squared plus 2x, we want to take its derivative. In the past, I've written it down as taking the derivative d dx of both sides, like so. When you take the derivative of this side, we said that y becomes y prime, and we take the derivative of each of these terms individually. X squared becomes 2x, and 2x becomes 2. And that is your answer. All of this is still true, all of this is still good, but I want to talk about the notation happening here. In general, when we have y prime, that's the same as a very infinitesimally small d, change in y, over a very infinitesimally small d, change in x. And so when we're taking y prime, we're really finding the change in y over the change in x. A very small change in y over a very small change in x, because remember the derivatives measure slope. So if you could please take out your section 4.9 notes. This section is not included in your textbook, ladies and gentlemen, so any sort of support material you would need, please see me for. I'm happy to provide it, but you will not find it in your book. This chapter is going to be dealing with derivatives in terms of more than one variable, but taking, well, I should say it's going to be taking derivatives of functions with more than one variable, but then doing them all in terms of a single variable, in our case today, x. So let's take a look at example number 1. Find the derivative of y is equal to 2x squared plus 4. So to do these, ladies and gentlemen, I want to get in the habit, especially for implicit differentiation, to be writing y is equal to the original equation, 2x squared plus 4, leaving a little bit of space here and here. Because what we're going to be doing is we're going to be taking the derivative in terms of x, and we're going to be finding the derivative in terms of x of this side of the equation as well. Anything that's done to one side has to be done to the other side by the properties of equality that we know. The derivative of y in terms of x, instead of writing y prime, I want to write instead dy dx. They mean the same thing, but this notation is going to be more helpful to us. So dy dx is equal to the derivative of 2x squared is 4x. Now we've never written this before, but if the derivative of y in terms of x is dy dx, then the derivative of x, a function, in terms of x, is dx over dx, a change in x over a change in x, and then that is plus 0, because the plus 4, the derivative of a constant, is 0. Notice, we've never written it before, and the reason why we've never written it is because dx over dx simplifies to 1. So dy dx is equal to 4x, which is exactly what we've been doing in the past. I would also like to point out over here that if we were taking the derivative in terms of y, what's the derivative of y in terms of y? Well, that would just be 1 if we were taking the derivative in terms of y. That's going to be the context for this next problem here. Find the derivative of y squared is equal to 3x to the 4th minus 8x. Notice that the big difference here is instead of a y equals, we now have a y squared. So we'll go ahead and we'll rewrite our equation as y squared is equal to, and then we'll leave a little bit of space, 3x to the 4th minus 8x. We're taking our derivative in terms of x, unless otherwise noted. So the derivative in terms of x on this side, and the derivative in terms of x on this side. This is where things get a little bit different than what we're used to. The derivative of y squared, if we were just looking at derivatives in general, is 2y, because we carry the power down, and we get 2y to the first. But notice that we took a derivative in terms of x, so we have to account for that by multiplying 2y by dy dx, as shown. That's going to be equal to the derivative of 3x to the fourth in terms of x, the 4 comes down, and we have 12x to the third, times the derivative of x in terms of x. Remember that we haven't been doing this in the past because they cancel to 1 every time, and that will still be the case. You don't have to do this every time. I'm just showing you now that this and this happen, and what usually happens is the dx's cancel. And so 12x squared times dx over dx minus the derivative of 8x is 8 times dx over dx. And if you remember, we had 2y dy dx is equal to, let me check, 12x cubed times dx over dx. And it was a plus or a minus, I don't exactly remember. It was a minus 8 dx dx. We're looking for the derivative in terms of x. So essentially what we're looking for is we're looking for this expression here isolated. And so dx cancels, dx cancels, and this doesn't go away because dy over dx doesn't reduce into anything. And so over here we're now left with 2y times dy dx is equal to 12x squared, x cubed, minus 8. Make sure that I'm saying that correctly. Yep, all that's good. I want to now isolate dy dx because that's what I'm solving for. This is the derivative. So I divide both sides by 2y. 2y over 2y is 1. So I end up with dy dx is equal to 12x cubed minus 8 all over 2y, which we can improve because 2 is a common factor, and so we end up with 6x cubed minus 4 all over y. Now you'll notice that this final answer here, this derivative, y prime, or dy dx, has both an x and a y in it. So to solve these problems, and in terms of context, our initial problems will have to have an x and a y present. When we work in class on these examples, you'll see what I'm talking about. But it is okay to end up with your derivative dy dx equal to an expression with both an x and a y. So let's take a look now at example number 3, which is the same concept, except we're going to make the problem a bit trickier. We're asked to find the derivative of x times y is equal to x minus 4y squared. To solve this problem, we're going to set it up exactly the same way we set it up before. To give myself some space, I'm going to work on this smartboard sheet here, but you can work below the problem, that's no problem. And so xy is equal to x minus 4y squared. What I want to do now is take the derivative, d dx, of both sides. So I'm taking the derivative in terms of x of both sides. Now this is an expression where two functions, x and y, are being multiplied. So I'm going to need to use product rule for this side of the equation. So what I'm going to do is I'm going to set up my u, I'm going to set up my v, I'm going to set up my u prime, I'm going to set up my v prime. In this case, u is x, v is y. The derivative of x is 1 dx dx, but remember that dx cancels, so it goes away. The derivative of y is 1 dy dx. So I write it as dy dx. And the derivative of this entire side is uv prime, in this case x times dy dx, dy over dx I should say, plus vu prime, 1 times y, which is y. And that's equal to the derivative of this side. Well, the derivative of x in terms of x is 1. The derivative of negative 4y squared. Well, the derivative of negative 4y squared is minus 8y. But remember that we're taking the derivative in terms of x, so we multiply that by dy dx. Just take a moment, look at that, see where it came from. And now what I'm going to do is simplify the problem because I want to solve for the derivative dy dx, which is the change in y over the change in x. So I'm going to go ahead and I'm going to subtract y from both sides. And I'm going to add 8y times dy dx to both sides. These are just expressions. They may look complicated, but they're just expressions. And so I'll go ahead and add 8y dy dx to both sides. This cancels. this cancels, and I'm left with x dy dx over dx plus 8y dy over dx. And that's going to be equal to the expression over here, 1 minus y. All I'm doing is some fancy algebra. Now you'll notice that in both of these expressions I have a dy over dx and a dy over dx, so I can now factor that out. And so I have dy over dx times the expression x plus 8y is equal to 1 minus y. My goal is to isolate dy over dx, so I'm going to divide by x plus 8y on both sides. That's 1. And so I end up with dy over dx, the derivative of y in terms of x, is equal to 1 minus the expression y over x plus 8y. Now I've included parentheses on the bottom, so I'll include parentheses on the top as well. It doesn't make a difference because the fractions obviously have parentheses assumed. But either way, the derivative of y in terms of x is equal to 1 minus y all over x plus 8y. Now once again, in order to solve these problems in terms of a context, or to get a value out of this given an x value and a y value, I would need, like I just said, both an x and a y from the original function. And you'll see what I mean when we take a look at the work that I'd like you to do now on your own, and then also the work that we'll be doing tomorrow in class. So if you turn the page over, you'll see the perform the following on a separate sheet of paper. I only want you to complete number 1 now, and I'm going to do number 1 as well on the smartboard, and you'll be able to see the answer. But numbers 2 to 8, we're going to be going through the problem together. If you take a look at number 7, it says find the tangent line slope of y cubed plus x squared is equal to y squared minus 5y plus 14 at the point negative 3 comma 1. In this instance, I've given you both an x and a y coordinate, and so once you find the derivative of this expression using the method we just discussed, you'll then take this point and plug it in. So let's take a look at number 1. Let's go ahead and give that a shot. So on a separate sheet of paper, please write this function at the top, and then take a couple seconds now and you work on it. You can pause the video if you'd like, if you need a couple minutes. And I'm also going to work on it as well up here. I'll explain my steps as I go, and then we will compare our answers at the end. This one's going to require that we use chain rule since we have a function inside of the function. So remember, I'm taking the derivative of both sides, d dx, d dx. The derivative of this function is a chain rule problem. In this case, I have u cubed, where u is equal to y plus 1. The derivative of u cubed is 3u squared. The derivative of y plus 1 u prime, well, the derivative of y is 1 times dy dx in terms of x. The derivative of 1 is 0, so plus 0 is redundant. And we end up with the expression 3 times the quantity y plus 1 cubed times u prime dy dx is equal to, and the derivative of this side is 4x squared, 4x cubed rather, minus 8. And so that's our first step, and that gives us at least the derivative part. The second part, after we found the derivative essentially, is just using algebra to isolate the derivative so that we can use it in context. Now this one's nice and simple because this is 2 terms being multiplied. So I'm going to divide both sides by the 3 times the quantity y plus 1 cubed. I'm sorry, actually this should be squared, that was my fault. Y plus 1 squared. And then likewise, I'll be doing the same thing over here. 3 times the quantity y plus 1 squared. That reduces to 1, and I'm left with dy dx is equal to 4x cubed minus 8 all over 3 times the quantity y plus 1 squared. I can now use this derivative to solve for the slopes of the tangent lines at any point for the function, provided that I know what x and y are. You'll see that by itself, this method seems sort of rote and a process, but then in terms of variables like volume formulas or area equations, we'll see that these methods of differentiation are going to become very useful to us in problems known as related rates. So that concludes as much work as I'd like you to have done. This is the last one I'd like you to check and make sure that you understand how to do it. When we return to class, we'll be working on the rest of the worksheet, and hopefully you have a nice night. Thank you.